I started out with a simple goal to experiment with Toyota Prius gearbox and inverter and get it to work as an electric drivetrain using open inverter board. And let me tell you, it was a fun journey. I had to tinker and experiment with the Prius gearbox and inverter to get everything working smoothly. But then things took a thrilling turn when I came across a cheap Tesla motor on eBay. I could not resist the opportunity to take things up a notch. So my original plan was to go for Lexus GS450h inverter and the gearbox as a DIY EV drivetrain, with Mazda RX-8 as a donor car. I even ordered a Zombieverter ECU, the electronic board that can control Lexus GS450h inverter. But fate had other plans. Just when I thought I had figured it all out, I stumbled upon a listing on eBay where the seller was selling a Tesla Model S front drive motor at a price point that I could not ignore. I mean, the combination of GS450h gearbox and inverter would have cost me about £1,200, but Tesla motor and inverter was for sale at £700. It was like finding a needle in a haystack. I decided to risk it, so it does look quite worrisome to go for this one. However, the offer is too good, and in the end of the day, I think eBay is supposed to offer a buyer price guarantee, which I'm hoping will work in this case. And I've decided to go and buy it. So let's give it a try. Okay, I'm trying to authenticate this on my mobile. I'm not sure whether this is going to work. Approve transaction. All done. And I'm just going to say I'm authorizing the payment. The payment may be going through. Okay, your order is in. Right, well, I feel quite relieved. But at the same time, it just feels so scary. I could be wasting £700 on this. Anyway, now we need to wait and see what's going to happen. Of course, after I placed an eBay order for the Tesla motor, I needed to get a version of the open inverter board that will work with the Tesla small drive unit. I had downloaded the design files from Damien GitHub and went to GLC-PCB to get the board ordered. The design files were uploaded, but had come across a few component shortages. I managed to find substitutes for passives in the end, but I left with two components missing: the PWM driver and transistors that control pre-charge and main contactor. I have to hunt for those somewhere else. I was able to find PWM driver easily from Mouser, but as a power switch IC goes BTS133, I had to resort to going on AliExpress and ordering few of them from there. The good news, I already received an email notifying me that the shipment is coming. The bad news, I have to pay custom clearance, input duty and VAT, despite the fact that it's a second-hand item. And it looks like the number of bureaucratic procedures is also increased. I'm trying to ask the company that is doing the delivery to make a clearance for me, but I'm not sure whether this will work out or not. I will report on it as we go along. And would you believe it, it did turn up. And here we go, this is the motor behind me. The package with the motor arrived a week earlier, but I did not have an opportunity to start working on it. But once I had a little bit of time, I started unpacking the package with excitement and worry mixed together, compared perhaps with anticipation of a great Christmas present, while worrying that it might be just another pair of woolly socks. I was quite pleased with my initial observations, as there were no sign of any damaged parts. The only downside was clearly visible signs of the aluminium corrosion on some surfaces of the motor. And the great extra bonus, the high voltage cable was completely intact. And the good news, we have this mounting bracket, which basically mounts on this side of the motor. And this is fantastic because this will definitely help me with my project. This is the motor part and this is the inverter part. So we need to gain access to the inverter in this case. My goal for this task is to remove Tesla inverter cover, but to gain access to the cover I first will need to remove the cooling pipes and the black foam cover that isolates the inverter top. I also decided to remove high voltage cables to make my life easier later on. I realized how inadequate my tool was for taking the side bracket off. Tesla definitely required something a bit more powerful. At this point, surely you may say, now it's a time to remove the inverter cover. Well, unfortunately not quite yet. This little orange cup is covering the three-phase connection from the motor to the inverter. Until those three connections are done, it would be impossible to separate inverter from the motor. I tried poking this cup with a screwdriver. Fortunately, I discovered that it has screws fixing it to the motor before I managed to break anything. And of course Tesla don't want you to go there. Since you peel off the label, you are presented with lots of warranty void messages on the label itself. I have undone the screws and removed the cup, which gave me access to the three-phase cables coming from the motor. I removed the screws securing the cables for the phase 1, 2 and 3 to the inverter, and now we are ready to remove the inverter. After all this, unbolting inverter was a very straightforward exercise. The only sticky part was unplugging a temperature sensor connector and encoder connector that comes from the cable within the motor itself. With the inverter removed, I couldn't help but admire incredible level of technology Tesla had even in 2013 when this car was built. During the video, I was referring to this as an inverter cover because it's so small, it looks like cover, but actually this is the whole inverter in here, including power transistors, processor board and everything else. So these are three-phase output that actually go to the motor itself. Let's have a look and compare this with the Toyota Prius inverter. Ta-da! I'm even struggling to lift it up. So this is Toyota Prius inverter in comparison, only capable of 50 watt max. Compare this with Tesla, capable of 250 watt peak power. Now I can focus on removing the top board from here. I need to remove the whole bottom plate and the board together because the bottom plate has current sensors embedded in the plate and they are soldered straight to the board. So my task would be to remove the plate with the board and unsolder the current sensors. And to do this I will have to remove these as well. You might be wondering how much did this cost me in the end. As I mentioned in my previous video, I might have to pay import duty and VAT, which turned out to be not exactly true. I only had to pay a VAT. There was no import duty on this type of goods imported into the UK, so I ended up paying VAT. VAT was about 200 euros, which turned out about roughly 180 pounds-ish. So the total cost of this was around 880 pounds, which turned out to be quite a good bargain in the end anyway. My ultimate goal is to be able to drive the Tesla motor, and of course I won't be able to hack into the Tesla electronics and the software, so the idea is to replace the processor board with the open inverter board. So to do this I need to remove the board first. Unfortunately the difficult part is I'll have to unsolder the Hall sensors. The one little tiny problem is that these two Hall sensors are soldered into the board, and for me to replace this central processing unit I will have to desolder these sensors and solder them into the new board I put in. I found that the best way to get rid of protective lacquer would be to heat it up with the soldering iron and actually scrape it off while moving the soldering iron across those three contacts. Having removed the lacquer layer, I started to use lots of flux and sacking device to sack out all the solder from those connectors. Well, looks like I messed up really badly, guys. Unfortunately, I was trying to unsolder these sensors, the current sensors, and each of them has 4 pins, and I broke 1 pin of each sensor. I think what happened is that those pins are actually connected to the ground port. It looked like I didn't solder them, but when I was trying to remove the board, both of them snapped off. I had a good look at the sensor and I could not see any remnants of the leg remaining on body of the sensor, but I decided to remove it anyway. I used the scalpel to dig it out and see if there's anything left on the legs where I can solder in the metal pin. Unfortunately, the pin was broken right at the root of the casing and there was no even visible metal contact available where I could solder something in there. Well, what a day. Where do we go from here? No idea. So I'm at complete loss right now. In despair, I went searching on the Open Inverter forum and DIY Electric Car forum for replacement sensors. I also posted a question on the Open Inverter forum, but so far no one came back with any advice. And at this moment, help came from completely unexpected source.
If only someone had done all this work years ago and posted it on a video and the forum. The SDU current sensors are Melexis MLX91209CA, exact the same as Model 3 drive units, usually in stock at Mauser.
I had a quick look on the Mauser website, and yes indeed, they were available. The only one little niggle was that the right model was not there. But help came again from fellow EV conversion enthusiast.
I'm not sure if it helps, but I searched for 7.3 mV per millitorr and found AS Electronics seems to have them in stock.
And yes indeed, they were available, and I got them. Now, with renewed hope, I started to work on finishing the open inverter board, so it is ready when the sensors will have arrived. When I ordered the open inverter board for the Tesla small drive unit, a few components were missing. Apart from the connectors, of course, those were PWM driver and FETs that drive the pre-charge and main contactor. I have started from PWM driver. As the smallest component, it was fairly easy to solder. This one has a decent spacing between IC legs. At this stage I decided to actually test the board to ensure that both supply voltages are present, as I did not want to do any more soldering and find out that part of the board is not working. And also I wanted to make sure that I can program STM processor as well. I quickly hooked up 12-volt wires and connected to my power supply. So we are not consuming any current and power is zero. So this means that our voltage is not getting into our system. So what I need to do is to measure 12 volts on the input, and we are getting 1198, and we are getting only 0.6 volts after the diode. This means that this diode is maybe not soldered in correctly. So let's have a look and see whether we got the right polarity for this diode. In this case, the Schottky diode SS54B is used as a reverse polarity protection, and cathode, the negative electrode, should be connected to the electrolytic capacitor, while anode, a positive electrode, should be connected to the 12-volt source. I found that my board was assembled incorrectly, and cathode, the negative electrode, was connected to the 12-volt supply, and positive anode was connected to the capacitor. Obviously I needed to reverse the polarity of this diode. I decided to check the second Schottky diode in a schematic that was connected to the output of the voltage regulator, and to my disappointment found the polarity of that one was also wrong. I unsoldered both diodes, cleaned the pads using solder wick, and now soldered them back in, this time using right polarity. Right, let's give it a try. Power supply is on, enabling the power, and it's working. LED is on. Fantastic. Let's test the voltages now. This one goes to the ground, and this one goes to plus 4.98. Perfect. And now this stays at the ground point, and this will go here, and that supposed to be 3.25. At this point I noticed that my 3.3 volt supply was drifting, while the 5-volt supply was very stable. I observed it for a while, and I noticed that the voltage kept on decreasing. At this point I decided to check the schematic for 3.3 volt supply and make sure that all the connections are correct on the board. Right, I think I found another mistake. I suspect the reason why the 3.3 volts is dropping is because this marked side of the tantalum capacitor should be plus, and it should be connected to pin 2 of the regulator here. It's 3.3 volt. Wow, I'm beginning to think that this Tesla build is cursed. And I have to say that all my previous builds went rather smoothly. But in this case I'm enjoying solving these little problems and moving on to the next one. So I've decided to do my own little modifications and reverse the capacitor polarity. I removed the capacitor using the same method as I used for the diode and soldered back in reverse polarity connection. And after that I've added another link for the wire to connect to the ground point on the JTAG connector. Our pin is a bit more grounded now. Okay, now power supply is on, and first 5 volts, 4.97, and now 3 volts, 3.28, and it seems quite stable. Excellent, another problem solved. After last week's shenanigans, I decided to program Open Tesla inverter board before I start soldering any more components. This would allow me in a way to check if STM32 processor is working properly. As usual, I use ST-Link programmer to do the programming bit. As Tesla being a synchronous motor, it will require to use the Sine firmware rather than field-oriented control firmware I used for the Prius motor. First, I need to connect ST-Link programmer and load the bootloader. Program and verify. After this, I could program the Sine firmware and program and verify again. If programming is successful, first I should get the message in ST-Link utility, and then LED should start flashing on the open inverter board. Yes, that looks good. No surprises this time for me. Once I programmed the board and I could see that it was working, I could finish off by adding missing components. Soldering FETs is a bit more challenging. As they have rather large heatsinks, I had to cover the pad and FET backside with the flux and heat the pad for much longer to ensure that solder properly had flown into the pad. I continue my work with the board and I'm now doing the Wi-Fi module. So, that was brilliant, wasn't it? I continue my work with the board and now I moved on to soldering in the Wi-Fi module designed to use Olimex little module that plugs into the connector, but I don't really like Olimex because it's not easy to program them. You have to plug in additional interface here and it's a bit more elaborate. So I've decided to go to VMOS D1 Mini. Just a drop of instant glue and our little Wi-Fi module was securely attached to the board. Connectors, do I really need them? I don't know. Maybe I'm just procrastinating at this stage, but I have decided to solder them. As I justified it for myself, it will be easier to do testing with them. Perhaps I'm just stalling to delay the testing, who knows. The minor complication was that I needed to steal some parts from the Tesla board. I hope Elon doesn't mind. And that brought memory of those damaged sensors. But this time I took extra care, and the connector shroud and locking mechanisms were removed successfully. To complete my mission, I needed to fit a shroud onto newly soldered connector and fit the locking mechanism. Now I have external connector on the board. I need a receptacle part so I can expose some connections for testing. This means that I have to assemble Molex connector and crimp some wires. Well, let's get crimping. I cut some wires to size so I can have them as my testing harness. I can always extend them later if I need to. I'm not much of an expert on crimping, and I only had to do it once before when I was making a connector for the Toyota Prius inverter. But I hope that my crimping tool will be suitable for this job as well. The approach I take is to position the pin in the tool first and insert the wire once the pin is locked in the tool. What is critical is to choose the right size for the pin. I'm using 80 to 20 AVG wire pins, so I selected the middle crimping position, which is closer to 0.8 mm square. Once the wire is inserted to the right depth, I just squeeze the trigger. Sorry, I mean the crimping tool. And the job is done. Now all that is left to do is to insert the pin inside the connector and get locking mechanism in place once all the pins have been done. Excellent guys, our board is progressing nicely and it's almost ready for testing. I already have a connector and testing harness built up, so it plugs in from the back side of the Tesla board, pretty much how it goes into the inverter. And all I need to do is I will need to finish off and solder in the start ignition switch and start inverter switch. Let's crack on with that. Okay, the plan is I will connect the ignition switch coming in from this side, so the power will be applied here, and I want to transfer this power to another 2 or 3 connectors here, and these 2 would be our ground. First we connect pin number 13, which is power, so it should be distributed through all of those 1, 2, 3 and 4. So this is pin number 9, and that goes to start button. turn here, it will go into position 2 in this case. And of course the last thing we need to wire up is to wire up the ground. Thank you for watching. I hope you enjoyed this episode. Please like if you did. Please subscribe if you want to see more, and more Tesla shenanigans next week. I will see you then.